In this study, initially, low-energy laser pulses of energy 270 microjoule per pulse was used to avoid severe overkill of the breakdown zone, and to minimize the energy loss due to shock wave propagation, which accounts for 50 to 70% of the total absorbed energy. But unfortunately, with low-energy laser pulses, no display of ignition was observed even though it fulfills the threshold conditions. Therefore, the experiment with low-energy laser pulses raises some question to our current understanding. Table 1 here is the laser beam parameters of the present study, and Table 2 presents the threshold condition from various literatures. After comparing the Table 1 and Table 2, it can be seen that values are higher for the present study. In the literatures, minimum ignition energy associated with the laser-induced spark ignition is defined as the amount of laser energy that is absorbed by the breakdown spark. Still, no ignition was observed after fulfilling the criteria of minimum ignition energy. Therefore, this study suggests that breakdown spark is not sufficient to create the ignition. However, it is only a necessary condition for its occurrence. This study also questions the definition of minimum ignition energy, and the reason for questioning the definition will be discussed next. Here, Figure 6 shows the experimental images of breakdown spark in an atomized fuel-air mixture along with the schematic diagram, and Figure 7 shows the acoustic waveform collected near the breakdown spark created by low-energy laser pulses of 270 microjoules at 1 Hz frequency. With such critical evidence of breakdown spark, but zero probability of achieving ignition, the experiment with low-energy laser pulses raised the following questions. What is the minimum or sufficient condition to achieve the ignition with lasers? Is it minimum ignition energy or breakdown spark, or something else? In the further discussion of this study, this paper will try to answer all such problem related to physical phenomena along with some remarkable issues raised by some other pioneer researcher in this field. This paper will also try to give a view on such issues by providing supportive experimental evidence, by accompanying high-energy laser pulses. High-energy laser pulses were used for two purposes. First, to understand the challenges associated with low-energy laser pulses, and second, to understand the entire physical phenomena of laser ignition with the physical time of occurrence of each event. This video presents the ignition of atomized spray with the high-energy laser pulses of energy 50 mJ per pulse. After critically analyzing the ignition phenomena presented in this video, both the purposes were achieved. Low-energy laser pulses were failed to ignite the atomized spray even after fulfilling the threshold conditions, because the lifetime of spark was very small, that is in microseconds, whereas, in this study, it was found that ignition can only occur when the spark spans for at least few milliseconds. If the spark does not continue for milliseconds, then ignition will not occur even though after energy deposition, the energy left with plasma is higher than minimum ignition energy. This paper also discusses the spray formation process with its effect on ignition, blast wave characteristics of high-energy laser pulses, and the role of the third lobe on rapid development of plasma kernel, which enhances the mixing of the kernel with the combustible mixture, and lead to the ignition. Finally, this paper has summarized the phenomenon of laser ignition of the combustible mixture into 3 chronological stages with their physical time of occurrence.